I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll see and we'll discuss one problem using the base net. Before going into the base net problem, we'll see some interference problem. Consider the given joint distribution, and this we have seen it in the previous lecture. Toothache problem, toothache bar, catch bar. Here under toothache bar, catch bar, we have cavity and cavity bar. The discussions we had detailed discussions, we have seen it in the previous lecture. In this problem, we have been asked to calculate a probability of cavity given toothache bar plus probability of cavity given catch. So first we have to expand one by one. Probability of cavity given toothache bar, we will write it as probability of cavity here and this and given toothache bar divided by probability of toothache bar. So probability of cavity and otherwise we can call it as intersection toothache bar. Cavity where the cavity is present, toothache bar, this is the cavity 0.072 we are writing over here and 0.08. So toothache bar given common intersection values divided by toothache bar, all values we have to write 0.072, 0.008, 0.144, 0.5676. So if you are adding and multiply and dividing, we are getting 0.1. So the first part we got it 0.1, and the second part we have to get it. The probability of cavity given catch is equal to probability of cavity and otherwise intersection catch divided by probability of catch is equal to probability of cavity and catch. Probability of cavity and catch. This value and this value. 0.108 plus 0.072 divided by probability of catch. So probability of catch 0.108, 0.072 and 0.016 plus 0.144. We got it, and if you are adding all these values and dividing, we are getting 5294. So if we are summing up 0.1 plus 0.5294, we are getting 6294. It is approximately equal to 63. So this values here we are getting 0.63. Hope you understood this problem. And the next problem, by using the conditional probabilities to compute the probability of A is equal to true given X is equal to true, comma B is equal to false, and all the values are being given here. By making use of these values, we have to expand this, then we have to substitute, finally we have to get the answers. So to compute the conditional probability of A is equal to true given X is equal to true, comma B is equal to false, we use Bayes theorem and law of total probability. Law of total probability we are using it. Given the probabilities of A, X and B, we breaks the problem down step by step and considering the dependencies between variables. Since X and B are conditionally independent, given A, we can express this joint probability in terms of conditional probability. By applying these principles, we can determine the likelihood of A being true when we observe that X is true and B is false. To solve this, we first compute this joint probability X is equal to true and B is equal to false given different values of A. Using the given conditional probabilities, we determine how likely it is for these conditions is to occur when A is true and when A is false. Then by applying law of total probability, we find the overall probability of X is equal to true and B is equal to false across both cases. Finally, using Bayes theorem, we calculate desired conditional probability by dividing the relevant joint probability by this total probability. So if you are expanding this, probability of A is equal to true given X is equal to true, comma B is equal to false is directly proportional to A comma true, X is equal to true, B is equal to false. If you are expanding, it is equal to probability of A is equal to true into probability of X is equal to true given A is equal to true into what? Probability of B is equal to false given A is equal to true. Here probability of A is equal to true value is given 0.4 and the probability of X is equal to true, A is equal to true, the value is given it as 0.3 and B is equal to false, A is equal to true. So if you are subtracting this value 1 minus 0.5, we are getting 0.5. If you are multiplying all these values, we are getting 0.06. Similarly, we have to find out probability of A is equal to false given X is equal to true, B is equal to false. So if you are expanding this, probability of A is equal to false, probability of X is equal to true, A is equal to false. And here, B is equal to false, A is equal to false. So A is equal to false. What is the value? 1 minus 0.4 is equal to zero point 0.6. Here 1 minus 0.4. And zero point 0.2 is already given. X is equal to true and X is equal to. Next, probability of B is equal to false, A is equal to false. Probability of A is equal to this you have to keep as it is. Here the next value 1 minus 0.4 is equal to 0.6. So if you're multiplying all these values, we are getting 0.072. And what is the formula for this, the entire value? A is equal to true, X is equal to true given X is equal to 0.060 divided by sum of these two values. Here true and also A is equal to false. We have to add these two values. Finally, we are getting 0.45. Hope all you understood this problem. And next problem is very interesting problem. In this, we are going to find out in the Bayesian network given below, what is the probability that Mary calls given that earthquake has occurred and a burglary has not taken place. In a typical Bayesian networks involving burglary B, earthquake A, earthquake E, and alarm A, Mary calls M, and John calls. The probability that Mary calls given an earthquake has occurred and a burglary has not taken place. Probability of M is equal to, in this case, what is the problem? M is equal to true, given E is equal to true, comma, B is equal to false has not taken place. This is the problem. Can be computed using conditional probability rules. Since Mary calls based on whether the alarm is triggered, we first determine the problem of alarm going off. Given A is equal to true and E is equal to true and B is equal to false using the conditional probability table CPT for the alarm. We calculate probability of A is equal to true given the probability of B is equal to false, E is equal to true. Once we obtain this value, we use the probability of Mary calling given the alarm status. That we can write it as probability of M is equal to true. M is equal to true means what? Alarm will be ringing off. M is equal to true and probability of M is equal to true and A is equal to false. This may be happening along with the law of total probability to find the final result. So by substituting the known values from this all these tables, we compute the probability of Mary calling under the given conditions. This approach ensures that we correctly account for all possible cases where Mary could be alerted by the alarm and make a call. So in this case, Mary calls, earthquake has occurred, burglary has not happened. So how you are going to write? Mary calls given earthquake had happened and burglary has not taken place. So if you're expanding this, we will write it as probability of A given alarm rings for given A, that is earthquake happen, burglary not happen, into that is Mary calls alarm rings, earthquake happen, burglary not had happen, plus A bar, the opposite, A bar, E comma B bar into probability of Mary calls for not alarm calls EB. So by using the Bayes-Natt theorem, using conditional independence, Mary calls only depends on the alarm. So this we can write it as probability of A given E comma B bar into probability of, this part we will write it as probability of M given A plus probability of A bar given E comma B bar into probability of M given A bar. If you are substituting all these values from this table, E bar, here a alarm happen, E comma B bar. That is E comma E is true and B bar is equal to 0.29 we are taking. And Mary calls, once alarm rings, Mary, where is Mary? 0.70. Next, plus probability of A bar, E comma B bar. The same thing we have to write it, and 1 minus 0.29 is equal to 0.1 minus 0.29 is equal to 0.71. Here Mary calls but alarm not ringing, means 0, false condition, A 0.01. If you are substituting all these values, we are getting 0.2101. So in this question we have to understand very clearly, Mary calls when earthquake had happened, burglary has not taken place. You are getting the value 2101. So the next problem is, what is the probability of in the base network, Bayesian networks given below? And the problem is, what is the probability that Mary calls given an earthquake has occurred? In this problem, earthquake has occurred and burglary has not taken place. Clearly they have mentioned, but here it is specified whether burglary had happened or not. This we should know. What is the probability of miracles given that an earthquake has occurred? So to compute the probability that miracles given that an earthquake has occurred, denoted by probability of, how we are going to write in this case, probability of Mary calls, for give Mary, that is it is true and given is equal to true. We need to consider both possible cases of burglary, whether it occurs or not. Since the alarm is triggered based on both burglary or earthquake event, and Mary calls based on whether the alarm is activated, we apply the law of total probability by summing over two possible values of burglary. It gives the value. If you are expanding this case, probability of Mary calls earthquake, we have to combine all these values. This is our case, but we have to find out this earthquake had happened and burglary also happened. If we are expanding A given E comma B, probability of Mary calls alarm rings, or otherwise A bar EB into M into A bar. So if you are substituting EB alarm rings, the value is 0.95 into Mary calls, here this value 0.70, and here A bar EB. A bar EB means we have to subtract it from this 1 minus 0.95 is equal to 0.05, and Mary calls when alarm is not ringing. Here this value 0.1, and we got it Mary calls EB, and otherwise we need Mary calls when the earthquake occurred. We do not know about burglary had happened or not, so we have to include burglary had happened or not. Both the cases we have to include, so that only we are writing probability of B into probability of M comma E comma B plus probability of B bar into probability of M given E comma B bar. Burglary had happened or not. B means B bar means B bar. So if you are multiplying B is 0.001 into probability of EB alone we have to take. EB here we have to, from this we have to take EB 0.665, we have to take this value, we have to substitute, and the probability of B bar, probability of B means burglary bar, minus 1 minus 1 minus 0.01 is equal to 0.999. We are substituting probability of M given E comma B bar. Previously we found out, previous problem we found out 2101. This is a big problem, important problem also. 2101, if you are multiplying and adding, you are getting 21550. It is approximately equal to, here 4 digit alone we want, we will write it as 0.056. So this problem is, so they may be asking in different types of questions by using Bayes theorem. All four problems, I think everyone able to understand very clearly. The remaining problems will solve it in the next lecture. Hope everyone understood all four problems. Thank you.